Let us consider an example. Suppose I have 1 over s plus 1 times s plus 2. Now, we can split this up as 1 over s plus 1 multiplied by 1 over s plus 2. So, this f of s is the product of two functions, and suppose I call this 1 over s plus 1, the inverse Laplace transform of that is e to the power of minus t u t. Let me call this as f1 of t, or simply f of t. The inverse Laplace transform of this 1 over s plus 2 is e to the power of minus t t u t. Let me call this g of t. So, the product of these two Laplace transforms must correspond to the convolution of these two time functions f of t and g of t, because convolution product in the time domain is equivalent to multiplication in the transform domain. So, the inverse Laplace transform of that is f t star g t star, f t star times g t, f t star g t. So, that will be 0 to t. When there are no impulses present, we may start with 0 and t instead of 0 minus and t plus. We can simply say 0 to t of f of tau g t minus tau d tau. So, 0 to t f tau e to the power of minus tau u tau and g t minus tau. G is e to the power of minus t t u t, therefore, e to the power of minus 2 t minus tau u t minus tau. Now, in the range of integration, when tau goes from 0 to t, this is equal to 1, u tau is equal to 1, because tau takes only positive values of time, tau positive values, and u t minus tau also the argument, the t minus tau is going to be positive, because tau is going to be less than t, therefore, this is also equal to 1. So, we need not regard them, we need not pay any attention to them. Now, the integration is only with reference to tau, therefore, e to the power of minus 2 t is a constant as far as that integration is concerned. So, you can pull this outside the integral sign. So, you have 0 to t of you have u e of minus tau multiplied by e of plus 2 tau, therefore, it is e tau, e of minus tau multiplied by e to the power of plus 2 tau. So, e tau d tau. That means, this is e to the power of minus 2 t, the integral of this is e to the power of tau itself by 1 with the limits 0 and t. So, that will be e to the power of minus 2 t e to the power of t minus 1, and that will be e to the power of minus t minus e to the power of minus 2 t, and this is valid for t greater than 0, because in all our arguments, if t is greater than 0 only, we have assumed to take u t minus tau and u tau to be equal to 1. Therefore, for t greater than 0, it is e to the power of minus t minus e to the power of minus 2 t, and therefore, this particular Laplace transform has got by its inverse Laplace transform e to the power of minus t minus e to the power of minus 2 t. Now, we wanted to illustrate this as an application of the convolution theorem. You can get at this result even simply by considering this, by making partial fraction expansion, which we will talk about in greater detail later, but this can always be expressed as 1 over s plus 1 plus 1 over s plus 2, and you can write this as 1 minus 1. So, if you consider this, you have a common denominator, it will have s plus 2 minus of s plus 1, that will be 1. So, this is equal to this, and we know that the Laplace inverse Laplace transform of this is e to the power of minus t u t, and the inverse Laplace transform of 1 over s plus 2 is e to the power of minus 2 t u t. So, this is exactly the result that we have obtained here in a more direct fashion, in a simpler fashion. But I wanted to illustrate the application of the convolution theorem by considering this as a product of two transforms, and in the time domain it turns out to be the convolution of two time functions. This is a verification of our result. So, we have seen that the convolution in time domain corresponds to multiplication of the respective Laplace transforms in the frequency domain. As a dual rule, we have convolution in complex domain, convolution in S domain. This is called complex convolution. I will just mention this rule and leave it at that. We will not pursue this because it is rather difficult to apply, and we do not have really necessary to use this a great deal. Therefore, I will simply say that if you multiply two time functions f t and g t, multiplication in time domain corresponds to convolution in the frequency domain, f of s convolved with g of s. What is meant by this convolution in the frequency domain is an integral which is like this: 1 over 2 pi j c minus j infinity to c plus j infinity of f of z times g of s minus z dz. So, you do an integration of the product f z times g of s minus z, where z is a running variable, and therefore, this entire integral will be a function of s, and that would be the Laplace transform or the product of f of t g t. And we have to take c, the abscissa of convergence for this sigma c must be greater than the abscissa of convergence for the function f of t, Laplace transform of f of t, Laplace transform of g, and Laplace transform of delta f delta sigma f plus sigma g. This abscissa of convergence for the product f of t g t Laplace transform must be larger than this, all these. So, whichever is the maximum, that should be smaller than sigma c, and this contour integration c should be larger than sigma f, and then should be sigma minus sigma g. That means, actually what it turns out is we have to take this contour integration in a narrow band separated by two regions. But as I said, we will not pursue this. All we can say is that multiplication in time domain corresponds to convolution in the frequency domain. Those of you who are interested can look up the reference books on this, and you will get further details on this, but we will not pursue this. We will now take up an interesting application of the Laplace transforms, which we will also treat this as a property of the Laplace transforms of periodic functions of time. Laplace transforms are periodic functions of time. Suppose I have a periodic function of time which is given by like this: 0 to t naught, 2 t naught, 3 t naught, etc. This is f of t. Now, consider one period of this blank. This I will call this f t multiplied by u t multiplied by minus u of t minus t naught. That means, you are multiplying this by a gate function u of t minus u of t minus t naught, that is just a pulse like this of unit amplitude. If you multiply this with this, you get this. So, this we will call that f1 of t. So, if you take a single pulse, the variation of the f of t over one particular period only, if you know the Laplace transform of this, you can find the Laplace transform of this easily. It goes like this: suppose f1 of t has the Laplace transform f1 of s. that is a single pulse, let it have the Laplace transform f1 of s. Then what is the Laplace transform of f of t? F of t is this pulse plus second pulse plus third pulse. Each pulse is displaced by this by an amount equal to t naught. The Laplace transform of this is f1 of s. The Laplace transform of the second pulse, the variation over the second period, is f1 of s times e to the power of minus t naught of s. The Laplace transform of the third pulse is f1 of s times e to the power of minus 2 t naught s, and so on and so forth. So, the entire periodic pulse function will have 1 plus e to the power of minus t naught s plus e to the power of minus 2 t naught s, etc., and this can be put in the form f1 of s over 1 minus e to the power of minus t naught s. So, if you have a periodic function of time, you want to find out this Laplace transform, all you need to do is consider the Laplace transform over one period, or the variation over one period. If its Laplace transform is f1 of s, the Laplace transform of the entire periodic function is f1 of s over 1 minus e to the power of minus t naught of s, where t naught is the period of the particular waveform. To sum up, we have in this lecture considered further interesting properties of the Laplace transform. In particular, we have considered the Laplace transform of f t upon t. Given the Laplace transform of f of t, how we can find the Laplace transform of f of t over t. Then we considered the initial and final value theorems, which enable us to find out the initial value and the final value of function of time without from their Laplace transforms, without having to find out f of t explicitly. Then we also talked about the convolution properties. Convolution in time domain corresponds to multiplication frequency domain are the two particular transforms, and the convolution in frequency domain corresponds to multiplication in time domain. The latter one we said is of limited interest to us, and then so we did not pursue this in some detail. We also observed that if we have a periodic function, it is enough if you find the Laplace transform over one period, then you can use that information to find out the Laplace transform of the entire periodic function by multiplying that, the Laplace transform of one period, by 1 over e to the 1 minus e to the power of minus t naught of s, where t naught is the period of the periodic function of time. In the next lecture, we will work out several examples illustrating the application of the various properties that we have discussed so far.